I think my screen is visible pretty much well.
Yeah, it's visible.
Yeah, so hello everyone. As briefly introduced by Professor Deepak sir, and he's really, I'm really keen to speak about my work in this such a platform. Yes, I'm a final year PhD student, not much experienced, maybe little experience on this topic of video anomaly detection. And yes, so the today's talk or probably next 1 hour gonna be hover around this topic. So why we start with this slide such as video understanding is that anomaly detection has many meanings. Like it could be on the weather, it could be on the some sort of financial transactions on numerical method, but here we are more interested on something video anomaly detection, right? Like what is abnormal happening on a video recording, such as maybe the video is recorded from a surveillance from the dash cam of a vehicle. So everything related to video related anomalies, right? So okay, let's start. So when we talk about this video anomaly detection, what can we imagine? So one of the imagination that brings here is in on a typical CCTV scenario installed on a street. So if we look at the video when there is an accident, so for those frames where there is a abnormality or there is an accident, we want to assign them higher score. If we look at the plot, the growth of this kind of the red plot is like it is close to zero when there is everything is normal, but when it starts to gain the peak when there is some sort of accident. So this is a typical imagination we can bring for a anomaly detection system or automatic or automatic anomaly detection system, right? So here, are we only interested in this kind of traffic based anomalies? Not really. So everything that can happen in a real world scenarios, it can happen in indoor, outdoor, inside a store, on the street, on a smart city kind of a scenarios, right? And the source of this kind of abnormalities can come from CCTV. And if we look at this slide that briefly describe many of these kind of abnormalities events. So if we look at the shoplifting, someone is trying to steal a laptop, or maybe in a burglary somebody breaks the door trying to take some of these things. For abuse, like somebody is like hitting someone else and arrest. So are these anomalies are such a important thing? Yes, because it can really cause some sort of loss to the human life, to the property, or any kind of financial losses, right? So the idea is to detect them in time when we are observing them, and to maybe to minimize the losses that can cause due to this kind of anomalies, right? So when we talk about these anomalies, is it really that easy to detect, or is there some sort of a challenging things? So the first thing is, when we are dealing with this kind of CCTV based scenarios, the CCTVs are kind of installed on a street or in a shopping mall, and they're constantly recording. So mostly the videos are untrimmed. So when there is a untrimmed videos, and if we want to train any kind of a machine learning or deep learning model, I hope you might all know that there are three kinds of scenarios. Like one is a supervised setting, unsupervised setting, and semi-supervised setting, right? In the supervised setting, for an entire video, you need frame level annotation. That what we call it as a temporal annotation. Like if you have a video of 1 hour and the video is recorded, let's say 30 frames per second, then you need to annotate 1 hour videos. The number of frames should be like 30 frames per second, and the total duration in seconds. So it's a huge lot of frames to annotate, which is really costly. And at the same time it could be error prone as well. Like the starting and the ending of the anomalies could be slightly different from different annotators. So how to tackle this kind of thing? So if we do not have any temporal annotation in videos, is it still possible to train a model? Yes, with a video level annotation. Like if you have in a video, in 1 hour video the anomaly is somewhere around 2 seconds, then you entirely annotate the video as 1 hour video as anomaly. So that brings us to this kind of weakly supervised setting. So which is one of the cheaper way of annotating the videos and then train the model in a cost effective way, right? So we are kind of avoiding the human labor and kind of enforcing the machine or the system to learn by from this kind of weak supervision. So this is one of the challenge when we look at this kind of data sets. The second thing is the sparsity of the anomalies, right? So the sparsity is like, as I say, if there is a video of 1 hour, maybe the anomaly happens just for 2 seconds or 3 seconds. So which is really a skewed distribution if we look at the number of normal frames to the abnormal frames. So how to learn a robust anomaly detection model that can learn from this kind of skewed distribution or really sparse data. And the third thing is the human centric fine grained anomalies. So if you look at the previous frame, whenever there is a kind of this kind of explosion or road accident or arson, so these kind of anomalies have a real impact in the scenarios. Like if we look at the anomalies, the scene before the anomaly and the scene after the anomaly is completely different. So there is a drastic change in the, or there is a drastic shift in terms of spatio-temporal cues. So these are mostly called as scene-centric anomalies, and these are mostly kind of easy to detect because the sharp change is pretty much visible. But when it comes to human centric anomalies, these are very much fine grained. So it's really hard to discriminate people buying in the store and people doing shoplifting, because the shoplifter, they mostly get blend with the normal people and still able to steal the things and uh, kind of get away from the scenarios. So how to deal with those kind of human centric fine grained anomalies is one of the biggest challenge, and having precision on those cases is really hard. And the third is something like long and short duration anomalies. Like some anomalies are very fast. Like if you look at this kind of accident, a bus ramped over someone, it's really fast. But if somebody is stealing a bike, it's a long activity. It's like the person gonna arrive in the camera field of view, look at the different scenarios, look around for other people availability there. Then the bike stealing activity starts. So these are long activities. So how to design a unified system that has the robustness towards both short and long activities? It also a very challenging task. So these are the maybe there are many other challenges in this domain, but these are the most four prominent challenges that the current days anomaly detection framework that has to tackle this kind of these four major challenges. So yes, as I say, I'm in my final year of my PhD. Towards my this objective, I have compiled a couple of papers, maybe two WACV, one CVPR highlight, and one ICCV highlight. But I want to speak about two papers that has achieved some sort of a robustness in this kind of anomaly detection methods. So one is that starts with the CVPR highlight one, and then we go to some sort of a WACV one that deals this kind of anomaly forecasting. Can we forecast this kind of anomalies, right? So let's begin with the first work. So the paper, it says that just dance with pi. Maybe the name sounds pretty much fancy, but the core problem that we want to solve in this kind of thing in this work is that how to use multimodal information or multimodal cues to achieve robustness in the weakly supervised video anomaly detection, right? And let's see that. So one of the motivation of this kind of work in the CVP, or what we try to do, is that uh, so in the surveillance system, if we want to really detect this kind of complex anomalies like shoplifting, like the human-centric anomalies, those are really complex and get blend with the other normal things. So how to achieve robustness in that? So the first one is RGB only features. If we look at just the RGB frames, for example, like if we look at the second row in the figure, the shoplifting, it's rarely visible that somebody is doing a shoplifting. So RGB only feature is not expressive enough to distinguish between this kind of complex anomalies and other visually similar normal events. So how to achieve robustness in this kind of system? So the idea is to augment the RGB, like, okay, we still need the RGB, we cannot discard it. So we augment the RGB with additional modalities, right? So that's the core idea of any multimodal system. But the first critical question that arises over here is how many additional modalities. So many state of the art exist. Maybe the talk I was listening before, they're also professor trying to talk about this multimodality. But how many really additional modalities are required to achieve the best performance or the maximum robustness in the system? So maybe the first one, the pose, because pose can, or the skeleton, human skeleton can give us some information of the fine-grained human movement. So here we are talking about fine-grained human activities, right? So for example, like for typical scenarios, if we have the pose, the skeleton, so the skeleton is quite invariant. So if we look at the skeleton, it doesn't depend upon the background, whether it is indoor, outdoor, it doesn't matter. It's just the skeleton on a XYZ plane. If it is 2D, XY plane, right? So it has invariant features, and at the same time, it has some sort of a salient cues for fine-grained hand movements, like somebody is picking something from XY location and putting somewhere there. So these kind of movements are mostly captured by the skeleton movement, right? By the skeleton. The third one is the depth. The depth is the second one is the depth. So in the depth, when we are talking about a CCTV scenarios, we are more interested in the 3D world. So the depth can give us that, okay, which entity is how much distance from the camera placement, like how, what is the distance between the other entities. So the depth information can give you the entities or the agents placed in the scenarios, and what is the distance among them in terms of depth map, right? So this is also very much critical information. The third one is the panoptic mask. So as we know, the anomaly is very much subjective, so we need to know that for example, like road accident cannot happen inside a shop, right? So the road accident has to happen in a street or on a highway or something like that. So it is very much context information to know that where we are, what is the surrounding agents we have. We need the panoptic mask information, like what are the objects around me, where I am. For example, like the third one, arrest. So there is a car present there, so we know that yes, this is somewhere around the street. But for the second one, there is tables, there is laptops, so it's much more closer to a shop scenario. To define the scenarios, we need this kind of panoptic mask information. So this brings us to the third modalities. The fourth one is the optical flow. So optical flow is very much on the global motion information. So to know that what is the dynamics of my scenarios, how many people are there, how many people are has a higher dynamics of motion. So to capture the global change in the motion. And the fourth one is the kind of language based semantics. As we know that on the recent days, many methods like LLMs, VLMs has a high level of language semantics that boost the performance. So it also kind of supplements the context information that we obtain from this kind of a panoptic mask. So here, by having more than 4 or 5 modalities, the main focus is to enrich the context information as well as the motion information. Maybe it is a local motion captured by the pose or global motion captured by the optical flow. So why this method is pretty much different from many of the state of the art is that most of the state of the art, they are limited to RGB plus one modalities. Like they are very much restricted to either RGB by pose, RGB by depth, or RGB by optical flow. So there is a scalability issue in the existing multimodal method. So here we are kind of proposing a method where you can inject or bring more than 5 or 6 modalities on a scale and still able to leverage this kind of complementary information in the multimodal feature space, right? So we'll see how many modalities we can do. So essentially it can go up to 6 or 7, but in the CVPR we can talk about 5. So, so where is the difficulties? Are we the first one to do this kind of job? No, not really. So this is the image bind people from Meta. So they have this kind of, they have started this kind of idea of multimodal, like 5 or 6 modalities, joint representation learning. But these kind of models are very much trained on huge amount of data set, like very large scale data set, billions of, like if we talk about the clip, like 400 million image and text pair. And those kind of facilities are not really present in the anomaly detection domain. So what we have, the mostly the difficulties arise by training this kind of model is we have limited data, we have limited supervision, like as I say, weak supervision. There is a disparity among modalities, like one modality is far away different from each other, like the pose that is capturing the subtle motion, the optical flow is capturing the global motion, so one is far away different from other, right? The third one is the noise and redundant information. So when we are bringing these five or six modalities in the into the system, so there is a level, there is a certain degree of noise. Maybe one is a kind of not going along with the other modalities, and there is also a redundant information. So how to control that? And the fourth one is how much we achieve the robustness, how much we claim to achieve the robustness by adding multiple modalities. If we are using this many modalities during inference, nobody gonna use it. Nobody is happy to use it. So how to control this kind of inference overhead is also a very much tricky thing. So our idea is to look at these four limitations and provide a method that can provide a method that can have some sort of a potential solution to this kind of drawbacks. So the first, if we look at the framework on the left, so the framework, if we have a set of RGB frames that goes to any kind of RGB encoder, you can imagine from starting from a VGG to the I3D to the recent days backbone like video MAE, clip, anybody. So you have a RGB encoder, and with these RGB features, some sort of any video anomaly detection method. It could be a transformer based, CNN based, and we are expecting this VAD model to be uh, give some sort of a higher score for anomaly frames, right? So if you add this kind of multimodalities to this system on the top, mostly previous method can be imagined that from the RGB, you try to estimate all these five modalities and then inject back to the VAD. But it has many other issues as we talked before. So how to reduce this kind of inference overhead? Because if we want to use all this multimodality estimator at inference, it brings a huge lot of cost at the inference. So how to do that? How to control that? The first idea is to generate pseudo modalities. Okay, we want to use estimator during training. On the bottom, if we look at this pivot, so the dotted line says that during the training from the RGB, we estimate these multiple modalities and use these multiple modalities as a pseudo ground truth to generate all these modalities with a cap, with a hat on the top. You see, so we take the RGB embedding from the RGB encoder and use all these multimodality estimator as a ground truth to generate all these pseudo modalities. And these pseudo modality generators are back to the are injected back to the VAD. So by this, we do not need all these multimodality estimator at inference. So right from this RGB, we can generate these modalities at inference, right? And we use them. Second thing is how to control the noise and redundant information. So when we use multiple modalities on a scale, so there is a noise and redundancy. So if we do this kind of generation from the RGB modalities while being task aware, so there is a loss function for the VAD model at the end, and that gradient is back propagating through the VAD to this generation module back to the RGB encoder, right? So while being task aware generation, for example, if we generate some sort of a noisy multiple modalities here, so it gonna translate to the VAD performance, the anomaly scores, and there the gradient will penalize the network and it's gonna guide the generation module, right? So, being task aware generation really helps in controlling the noise and redundant information to identify the network, which modalities to be, which redundant information to be suppressed and which noise to be suppressed, so that you have higher detection accuracy. The third one is the disparity among modalities, right? So when you have five or six modalities, if we, for example, if we have all these five modalities embedding one after another, we concatenate them like regular feature vectors and then apply some sort of a contrastive loss. So contrastive loss is very much well known in kind of bringing two embeddings close to each other. So one of the very classical way of doing this kind of stuff. So if we concatenate all the modalities into one vector and then we apply contrastive loss, so mostly here in this case, the modalities that has the highest information content will only be bring close to the RGB, but all other modalities are those have less information content or let's say less dominant feature will not be participating in this kind of anomaly detection. So it's kind of the most dominant modality will only be participating in the anomaly detection and other will be remain overlooked. So how to handle this kind of situation is that if we dissociately apply contrastive loss instead of applying one contrastive loss for the entire multimodal feature vector, if we separately like pose with the RGB one contrastive loss, text with RGB another, panoptic mask with RGB another, so five separate way of uh, uh, combining the modalities by contrastive loss. So by this, the complementary nature of each of these modality will be very much well injected to the RGB, and it will enhance the representation of the RGB augmentation, right? And the fourth one is that the limit, how to tackle this limited data and limited supervision. So here, as of now, as we talk about this model, so we have a generation model, we have set of contrastive losses. So this needs a lot of data to train. So how to do that with limited data supervision is to follow a teacher-student paradigm. So the teacher-student is like first so it is mostly on the two step. Like we have a first step of training a teacher model, and then keeping it as a frozen, and then using the student model with this polymodal inductor to enhance its representation ability. So maybe I give it too much information in one slide, but let's go into the details of this framework. So if we look at this PyVAD, the core of this PyVAD is a polymodal inductor, right? So if we look at the framework, as I say, there is a pre-trained teacher, there is a random initialized student, and this polymodal inductor can be placed between any two blocks of this kind of student, right? So let's imagine the teacher is a sequential set of blocks of transformer that we call it as a VAD model, and this polymodal inductor can be placed between any consecutive blocks like I and I plus 1. So, and these both teacher and student, they take feature from the I3D encoder, right? So, but what we essentially we have seen is that placing this polymodal inductor only in early and later stage has more meaning, or it's a more cost effective way, because the features in the early stage is very much basic and more close to the representation of the video, and the feature in the later stage is more translating towards the anomaly scores. So having or augmenting the multiple modalities only in the early and later stage at the it make more sense there, right? So how this polymodal inductor it takes? So it basically takes the RGB representation, let's say F star, from a ith block of the student, which is randomly initialized. With this feature F star, it gives it to a pseudo modality generator. The pseudo modality generator generates all these modalities with the cap, and once these are generated, the same RGB feature is applied is added there with the contrastive loss by different dissociative contrastive losses to get a further augmented RGB representation. But right now, uh, how would we know that the association, the multimodal association, what we did over here, this is correct or not? To guide this kind of, or to ensure that there is a correct association of multimodal feature along with RGBs has happened, we apply a distillation from the teacher model. So we take the same feature vector from the same layer of the teacher to say that if because the first one is already pre-trained on the VD task, so it pretty much well known about which frame is normal and which frame is abnormal. So this is kind of guiding the association, guiding the correct association of multiple modalities to the RGB. And upon this distillation, the modulated feature vector f star m is injected back to the next block of the student, like I plus 1. And this process goes on in the early and the later stage. If we zoom in this kind of framework a little bit, so the polymodal inductor, if we look at, there are two key modules. The first one is the pseudo modality generator, the PMG. So all the blocks in the green boxes, inside the green boxes, is the pseudo modality generator, and all the modules in the red boxes is the cross modal induction. So basically, if we look at, we have, let's assume that we have the student RGB f star. It goes to the PMG is basically an encoder decoder structure. It could be imagined with any kind of diffusion model or GAN model to bring. So essentially, here we aim for a simplicity. Can a simple model still be able to generate this kind of modalities, right? So first, the student RGB is given to a shared encoder. So basically, it kind of do encode the RGB to some latent vectors, and there are 5 parallel decoders. So each of these decoder is guided by the pseudo modalities ground truth that we get it from this kind of foundation models. So pose is kind of yellow V7 pose. Depth, what we obtain is from the depth anything. Text, we get it from the V5 clip. Motion is raft. Panoptic mask is, I think, it was SAM model, the segment anything. So these embeddings obtained from all these foundation models are used as a ground truth. So this ground truth is helping to optimize this decoder. And once these decoders are optimized, we are able to get this kind of different pseudo modalities. So basically, the network is trained in multiple stage. So on the first stage, we train this teacher network. Then we keep it frozen. On the second stage, we unlock this pseudo modality generator, basically the encoder decoder. And once these are pretty well optimized, then we unlock the other part, the cross modal induction. Because if we unlock everything at once, so all the things are pretty much random, so the optimization will not work very well. So it has to go through multiple stages of training. So once these are generated, then the third part is unlocked, like the cross-modal induction. All these multiple modalities are given to some projection F1, F2, up to F5. Then we apply standard loss of influency, that is the contrastive loss. Maybe we'll talk about the losses in the next slide. So as we see, individual cross-modal inductions are happening parallelly. So basically here we are kind of taking the student RGB and applying this kind of contrast based augmentation. And after these, all these augmented latent vectors are stacked. So basically now the time is to find out the relation between multiple modalities, like how pose is related to the depth and how is it related to the optical flow. And that is well done by the transformer, like what is the relation between the long-term tokens and the short-term tokens. So there is a stack of transformer layers here, and here we try to do some sort of a skip connection to still see the relevance of the RGB. And once these features are being modulated after the transformer, then this is the time for distillation to see that if whatever the augmentation is being done by this cross-modal induction, whether it is in the correct, or is it being optimized for a anomaly detection objective or not. And to ensure that, we have the teacher model RGB here, and then this is distillation is happening, right? And then we get this kind of F star M. So to look at more on the optimization side, so basically as we see, we have this kind of encoder decoder structure. These are basically the loss of PMG. The pseudo modality generator is a kind of a reconstruction loss. So it's a standard reconstruction auto encoder style reconstruction loss. So you basically try to minimize the original ground truth embedding that belongs to pose, depth, mask, optical flow, or text to the generated one. So there is a sum over 5 for all the 5 modalities. The standard influency loss is that uh, this operates across time. So basically, if we have a RGB student app star for the time TI, so we want to minimize the embedding space, embedding separation for any next modality of the same timestamp, like for frame I to frame I, like ith frame of RGB, ith frame of the pose or anything, any other modalities, and then we want to minimize the distance, and we want to keep all other snippets, other modalities, like for example I plus 1 or I plus k, we want to maximize separation. So it is kind of the same frame, different modalities are being minimized, other frames, same modalities, other frames, other modalities are being uh, separated. So this is a standard info NCA loss, and we apply it for all these five modalities. So there is a sum over five, and the distillation loss is also very much similar to a reconstruction loss. So basically, we are trying to minimize the multimodal feature what we get from this the transformer, and with the teacher model to say that the multimodal feature has to come close to the teacher, and we want to normalize by the embedding dimension, right? So, by doing such a task, do we really achieve some sort of a precision in anomaly detection? Let's look at that. So, we kind of evaluate the framework on very much benchmark data set like UCF crime published in CVPR 18, XD violence, ECCV 20, and this is MSAD nearest 24. So if we look at that, when we use only RGB at inference, because we are using RGB at inference, on the standard AUC metric, we are 2.75 improvement. But if we look at the abnormal metric, like AUC abnormal is only evaluated on the abnormal videos, right? So on AUC, you have both normal, abnormal, but on AUC abnormal, you just have only abnormal. So here we kind of achieve 7% of performance, 6.96, close to 7. So it means that there is some sort of a robustness in the system that has higher understanding of abnormalities, but thanks to this kind of multimodal information. And this kind of performance we achieve across all these three data set. But if we look at the slightly, if we zoom in the class level accuracies, so if we look at some of the classes, let's say explosion, the existing state of the art, let's say URDMU is pretty much standard at that time. So they have 0.47, like 47% accuracy, but what we is kind of almost double the accuracy, like 78%, or there is a significant boost across classes like fighting 79 to 91, shooting, shoplifting. So there is a significant gain we see across. But is it the end of the task? No, not really. What we observed is that if you look at these plots, uh, look at this table. So this is ablation study for each of these modalities, and we look at that. Yes, on some cases the motion is pretty much relevant. So all these modalities bring some information, but the highest information that brings is that the depth. So from the top row it is only RGB. So if we look at 70 and 75, like 5% gain, it is pretty much really high. uh, okay, the next question is, do we really, is it the optimal way of combining all these modalities? Not really, maybe. Maybe one of the best until now, but is it the optimal? May not be. Because why I say so, if we look at that, when we combine all these five modalities, the green boxes says that these are the classes where we see the improvement, and all the red boxes, these are the classes where we see the decline in the performance. So it means that there is still much of a way to go to see if all these modalities, so here the true complementary nature of the multimodality is not being explored. Yes, it achieves something, but not the optimal one, right? So if we look at the qualitative results here, so we exhaustively evaluate this kind of framework, like arson, burglary, road accident, shoplifting to everywhere. So if we look at that, we achieve very much precision in anomalies on many cases. So if we look at this activation of multiple modalities, how the modalities are being activated for some anomalies. So if we look at that, the depth information, the orange is always has a higher amplitude among all other modalities across the scenarios. So it means that depth is highly relevant for this kind of surveillance application. But at the same time, we need to also look at the notion of the curve or the notion of the plot for other modalities. So, for example, like pose, if it is a arson, there is a human involved. The pose has a notion of slightly getting higher activation for the anomaly region, like the blue part. If we look at that, there is monotonically going and then there is a sharp jump. So the if we look at that for the human centric, like shoplifting, the poses also has a higher activation. Same as the road accident, you have this kind of motion, the global motion. So uh, yes, there is a complementary nature of the multiple modalities are being exploited in this model, but still this is not the optimal, what I mean by. So in summary, for the first work, what we are trying to explain is that we have significantly improved this kind of VAD models and achieved pretty much decent accuracies. Uh, but there are still limitations that out of five modalities, only two to three or modalities are being prominent and other are being overlooked. And we still need to improve it. So as a next step, this kind of modalities can be used in LLMs or VLMs in a more cost-effective way. So this is maybe one part of my talk. If you have some question, I can take, or we can go to the next one. We can go to the next part of the talk. Can I see any? Do we have any questions? Okay, there is Sweta. What about audio modality? Yes, so we use the audio modality on XD violence data set. So on the paper we didn't mention, on the this slide I didn't mention, but we use audio. So the audio features are being taken from VGGIS model. Yes, audio is taken. Okay. Are weakly supervised annotations successful? Can you explain in terms of results how they perform in full? So in terms of state of the art, there is not much fully supervised data sets because nobody wants to annotate them, honestly. The data sets are so long, the videos are so long, nobody wants to annotate them. So all the state of the arts are mostly around the weakly supervised scenarios. Maybe there are small data sets, but those small data set it doesn't really replicate the real world challenges. So, but UCF crime is very much real world, and there is no much fully supervised annotation. So, can we just replace RGB with other modalities for computation relevance for anomaly detection? Can we just replace RGB with other modalities for computation? I think this question is not very clear. You want to replace RGB with other modalities for computation relevance. I don't think get this question. Sorry. What about audio? I think I answered this question. Okay, if you don't have this any more questions, we go to the next one. So until this part of the talk, we are mostly talking about anomaly detection. But there is another important part of this anomaly understanding is that can we guess the future anomaly, like the forecasting of the abnormalities? And this is the this kind of attempts uh, we make it in the last year or this year likely. So we provide a data set that can encourage this kind of anomaly forecasting in real world scenarios, right? So one of the motivation was that in mostly most of the related work either encouraging offline or online anomaly detection that can only give you some sort of timely intervention or some sort of investigative steps. But if we can predict the future anomalies, it can give you some sort of a preventive measure which can have a higher societal impact. But the first question is it really possible to predict all future anomalies? No, no, not at all. I mean, this is really a challenging task. But if we look at the abnormal human behavior, yes, it is possible. So why? Because when there is a human in the scenario, so for example, there is human on the street, human in the store, it try to interact with the surrounding agent, surrounding surrounding entities present, for example, like objects or other living entities. So by looking at this or by carefully observing this kind of interaction, human level interaction, it you can really analyze the early behavior of this interaction, and then maybe approximate that whether this kind of interaction can lead to some sort of anomalies in the future, in the near future, right? So for example, like arrest, so there is a human to human interaction. Maybe on the first few frames you see that there is an argument, people are facing to each other, there is argumentative behavior. Then in the next future frames you can say that yes, there is a kind of like a policeman argumenting with other guy, so you can say that yes, he gonna arrest or something like that. Or a shoplifting, like there is a human to object interaction, like somebody is looking around, looking at the object many times, or he's looking for other people availability there, and maybe you can predict some sort of shoplifting there, right? But the key question is, how far can you predict the future? Is it for the next 1 seconds? Roughly, cameras are operating in 30 frames per second, right? So, like predicting for the next 30 frames. Or is it for next 2 seconds? Three, maybe four, five, eight. So, can you predict 8 seconds after, which is pretty much far away? So, we will see in this work. So when predicting this kind of 8 second, next 8 seconds, so there is a high level of uncertainty. So if we look at this kind of framework, you have an observation past. So you're gonna observe certain amount of frames, and from the observation, the prediction or the anticipation gonna happen, right? So when we talk about longer future, there is a higher degree of uncertainty between the observation and the future event, right? So how to control this kind of uncertainty? So one way is to say that from the observation you have a past encoder. So the past encoder is mostly given to the future encoder. To in between them, there can be some sort of a uncertainty handling module. Basically, to say that whatever the past has observed is relevant, let's say theta one, and the second one to say that no, this is not relevant to the future, right? Something like don't trust the past, anything can happen in the future, something like this. So this kind of information, if we can embed to this kind to the past encoder feature, it might help in the future decoder, right? So okay, maybe if yes, what kind of anomaly, like sorry, what does it say? Okay, so what kind of anomalies? And the third one is like, is there a chance, if you talk about the long term anomalies, is there a chance that the same anomaly or other anomaly will happen in the near future? Like you really want to see the long future, right? So towards this, we propose a CAT models. I don't know how much time do I have. 20 minutes from now. Okay. So so we propose a CAT model. So basically, the CAT model is it's a past encoder. So what we try to see over here is that we want to really look at the human interaction or the object level interaction. How does it happen in the past, and does this kind of interaction has some sort of a pseudo knowledge about the future? So basically, it has a interaction module, that is the TIM and the OIM. TIM is mostly like temporal interaction, and OIM is the kind of object interaction. And between this interaction embedding, like E of T and O of E of O, there is a null model. Okay, the name doesn't say much about it. Null means nothing, but it's mostly the acronym of normalcy, uncertainty, latent learner. So basically, the past observation is mostly normal frames, and by observing the normal frames, can we predict the future anomalies, right? So let's say that you have some sort of past abnormal frames that goes through a clip image encoder. So whole frame, like it can be capturing the entire scene. So you have the feature of scene fs, And for the same set of frames, there is a mask transformer is applied to see that how many different unique objects you have around. So these are the mask of different objects. And the mask transformer also give you a dictionary of text level of objects, like it is a table, floor, people, book, something like this. So this kind of two information, the object mask and the object text label, can be used by the clip text encoder to clip text and image encoder to get the feature of object. So basically, if you have k objects along time t, so it is t by k by d0 is the embedding dimension, and same for the text. So basically the text information always it brings some sort of contextual semantics. And if you want to look at into the fine grained or more detailed information, it is the panoptic mask, the object mask. So it gives you the fine details, what is their xy coordinate location, where they are in the entire frame. So it's kind of more going in detail. Right. So in both part, if we look at one with one kind of information, we have the context information, and one is the fine detail. So here also the context information comes from the scene, fine details comes from the from the same object. Now the idea is to combine this kind of context information with the fine detail through this kind of interaction module. So basically, the f of course is the f of co is the course model that tackles this kind of course information. It is a regular transformer model, and g of phi is the another transformer model looking at the fine detail information. And the cross attention is basically associating how these kind of fine grain or the subtle movements are associated in the global or the coarse information. So this is the cross attention it does, and this cross attention it tackles around the t dimension, that is across the temporal dimension, to look at the temporal interaction. So the OIM is the exact replica of the TIM. Rather, it looks at the object level. So here it looks at the time axis. Here it looks at the object axis. How the, let's say, the table is interacting with other agent, like for example, like the human or the book or anything else. So these are this kind of information. It's the object level interaction. So after these two embedding modules, we get two embedding vectors. That is the embedding of T, embedding of temporal interaction, and embedding of object interaction. Right. Now the idea is to associate this kind of object interaction. For example, like one someone is reading book while somebody is
Your
approaching
screen
for.
is not, Stasis, your screen is not visible, I think. Everyone is asking.
Okay, how come it also happened in the last presentation? Okay, from where you people lost? Can somebody say?
Okay. The balance circle.
From 8-second slides. Okay, 8-second slides. Wow, far away. Okay. All right. Okay, so this is the slides. I think you people lost, right? Can somebody confirm? Okay, let me guess that yes, this is where everybody is lost. Okay, so here I was talking about the uncertainty, how to tackle this kind of uncertainty in the past observation to the future anomalies. And okay, maybe this is not so important. So here I was talking about how this temporal interaction. So let's assume that maybe you listen the audio, so it's not so difficult. So you have this kind of temporal embedding and object embedding. So the idea is to associate these object level embeddings, object level interaction to the temporal interaction, right? So so how to do that? So as I was saying that in the uncertainty modeling, the idea is to say that whether the past observation is related to the future or it is not related to the future. So let's have this kind of two kind of analogy to say that yes, it is related, yes, and no, it is not related, right? How to encode this kind of analogy into the embedding vectors? So basically, we give it to some sort of a MLP layers. We call it as a uncertainty alpha that gives us two different activation from the past observation. One is the P, to say that okay, this part of the past is relevant to the future, and second is that no, this part of the past is not relevant to the future. That is 1 minus P. And with to this kind of completely divergent analogy, we want to associate the object interaction. So again, these associations are mostly made through cross attention. So basically here you will have two embedding vectors, one object interactions that is relevant to the future, another object interaction that is not relevant to the future, right? And this kind of information is given to the future decoder. So basically future decoder, it takes some sort of anticipation queries, right? Something like if you want to predict next 8 seconds, put together 300 frames or something around 256 frames. So you will have 256 anticipation queries that goes through some sort of a mapping function, and then we apply this cross attention, like how each of these learnable queries are getting associated with these theta 1 and theta 2. And upon these two vectors are cross attended, like associated, then we concatenate and apply a classifier, this kind of the cross entropy loss based classifier to optimize the network. But the thing is how to ensure that which among theta 1 and theta 2 is relevant to the future, because we do not know. Maybe in the first iteration, the network randomly say that this part is relevant, this part is not relevant. Basically, we try to minimize the class level of the classifier to theta 1 and theta 2. If there is a smaller distance between class label or the activation in the class label to theta 1, then we know that theta 1 is relevant to the future activity. If it is not, then theta 2 is relevant to the future activity, right? So maybe there are other details of the smaller transformer model. I don't want to go in detail there. So, okay, as we were the beginners on this kind of topic, like forecasting abnormal human behavior, so we also provide a data set encoding this kind of human to human interaction, human to object, and human to all other. Maybe the data set is not so large scale, but it really depict the real world scenarios, like what are the things that can happen in the real world CCTV scenarios, right? So yes, towards benchmarking the data set, we run many of the benchmark state-of-the-art models, and we see that CAT is, and we evaluate them across multiple timestamps. So if we look at the short-term anticipation, like predicting the next 1 second, it has the highest accuracy. Like it's really kind of easy. But predicting the next 8 seconds, the accuracy is like 7 points less than the 1 second, you see. So or 6 point less than. So predicting the long term future is very much difficult. And if we want to predict this kind of long term 8 second, how many frames do we need to observe? So through experiments, we found that if we really observe 200 frames, maybe it is sufficient to predict the next 8 seconds. But if you want to really scale up the prediction for longer duration, yes, you need to observe more, right? So there are few qualitative cases. If we look at that, these are the ground truth for the next 1 second. Before that, everything was normal. Like for the fighting, Fiat kind of exactly match with the activation map of the ground truth on the human to human interaction, like somebody is fighting, right? Something like shoplifting, CAT is also pretty much well, because on these two cases there are fewer interaction, like one person is interacting with one, so these are one-on-one interaction. But when you have more complex, like human to object, like all kind of interaction, there is a dense interaction, the CAT is still not the best. Like something like a robbery, somebody is breaking the door, somebody is threatening, this kind of scenarios, CAT is not so well, because these are more complex interaction and you need to provide more specific details about this, right? So yeah, in summary, the second part, what we wanted to do is that, okay, we provide a kind of a affirmative task, the anomaly anticipation, to promote this kind of mitigatory measure in serious crimes. Yes, and we propose this kind of a SIAD model that it kinds of opens up new direction to analyze this kind of complex abnormal human behavior. And yes, it achieves kind of a competitive performance, but still there is a limitation, is that SIAD is very much confused between something like a stealing and robbery. Like for example, like the stealing could be encoded as robbery. Still it is fine, because that shows the seriousness of the model. But if a robbery is predicted as stealing, so it's kind of classifying a very serious crime or very serious anomalies to a less serious anomaly, like that. So it really affects in terms of primitive actions, right? So in future, maybe we will be using LLMs and VLMs to describe the anomaly. So in the last talk, if we are looking listening to the professor, the explainability. So how to see the explainability of these anomalies, of these serious anomalies, right? So that is the future scope of this work. Mm. And yes, as I'm a PhD student, finally in my final year, I have bunch of I have a lot of supervisors and my mentors, and I also collaborate with many people. So yes, if you gain some sort of interest in our work, yes, do reach me out for further and detailed explanation. And, yeah,
Yeah, I think there are a couple
yeah,
of
thank you.
questions in. Yeah,
Yeah,
there are
yeah,
a
yeah,
couple
sure.
of questions in the chat box. Yeah,
I already kind of answered few questions, like mostly Sweta, weak supervision annotation. I already answered these questions. Maybe there is new. What about the GPU performance for many modality inclusion? Maybe this question I didn't answer. GPU performance. What about the GPU performance for this many modality inclusion? So the GPU performance is it's only you would see the complexity in training, but at inference there is no additional modality is included as a foundation model. So we are basically generating them. So yes, in training you need A100s, the GPUs. Uh, Other than that, maybe it's really difficult to train these models. Yeah, yeah. So any other questions? I think I already answered this question, sir. If some any other questions, I'm happy to answer.
yeah. Participants, if you are having any queries, you can write in the chat box. Yeah, so I think there are no other queries from the participant side.
Hmm.
So let us now thank our speaker, Snehasis Maji, for his wonderful talk on video anomaly detection, which is a really very important topic, as we all know. Its importance, right? Not only in smart cities, but also in various places, various working places as well. So thank you, Snehasis, for accepting our request and delivering a wonderful talk on
Thank you.
video
Pleasure
anomaly
is
detection.
mine. Yeah, yeah, yeah. Thank you.
Yeah.
Yeah.
So, participants, we'll be having our next session at 6:20. That will be delivered by Professor Puneet Goyal from IIT Ropar. So, please wait for 5 minutes. He'll be joining us soon.